the two rules are that the rule for the root is that the root has a minimum of 2 children and a maximum of m children. Now there are 2 ways of implementing these trees. If we have a B tree of order 3, there are 2 ways to implement them. I just want to make this very, very clear. The relationship between the number of nodes and the number of keys is now not 1-to-1. With binary trees, for every node you have a key. But if you have a B tree of order 3, that means you could have up to 3 children. Now, in some cases, you can implement it with 2 keys, so that less than the first key is your left child, between the 2 keys is your middle child, and greater than the maximum is your right child. So you need 2 keys. You go to the left of them, between them, or to the right of them to go to the next node. Does that make sense? Okay, so that's the idea. But we can also implement them by, in this case, basically we don't replicate the keys. But the way I'm going to show you right now, and this is just another way, I'm going to show you both ways actually, is you can actually have 3 keys. And I'll show you how I'm going to do that. So what we're going to do is we're going to use a B tree of order 3, and we're going to insert this key sequence into them. One great feature about B trees is they are always balanced. Always balanced. They never get out of balance. Okay. So if I'm going to insert K, F, and G, I'm going to insert K, F, and G. I'm going to keep them in the right order. They're all going to go to the same node. They're all going to go to the same node. So what's going to happen is when I insert Y, Y is going to go here, but notice the node is bursting. It's too big. Can't take that. So every time a node is bursting, it's going to split. So when it splits, basically the FG and the KY split into 2 different nodes, and then we have to create a higher level. So what happens is we take the maximum of this one, maximum of this one, and put it like this. So notice the tree was balanced. Now it's still balanced, but it's grown a new level. And the growth occurs at the root level, which is different than typical nodes. And that's why you can see it stays balanced, because the growth is at the root level. That means nothing changes below in terms of non-balance. Next, we're going to add U, R, and W. So to insert U, notice that U can just go in here. R overfills this node. Okay? So this node is now overfull. And so what's going to happen with this node? It's going to split. When we split, you're going to go FG, KR, and UY. And then what's going to happen is, since I have 3 nodes, I need to have 3 keys in the root. So what's going to happen is that R is going to float up into here. Notice that I have a tree now still balanced. Okay, then I'm going to keep adding. So next I'm going to add to this, I'm going to add W and P. So W and P, W is going to go here, P is going to go here. Super easy, nothing is going to change in the tree. And then I have to insert L. So W and P here. Now when I insert L, it goes here. And so what happens now is this node becomes overfull. So what happens? Splits. So I have FG, KL, PR, separate node, UWY. And what happens is that key of this new split goes up to here. But then this overfills the node above it. So that one also splits into GL and RY. And so GL and RY, so L and Y, become the keys of the new root. Notice that this is the new tree. Now we're going to insert D. Where's D going to go? D is very easy. And now so I'm going to try to cut the time right now, basically. So you get the idea that the tree basically will split and grow up. And in the reverse, it's going to get what's going to happen when it becomes smaller and smaller. Basically, what happens is the root, when the root loses 2 values, it only has 1 value, the root is no longer necessary. We go down, and basically the tree shrinks by deleting the root. And another one takes the root. Okay, so that's that. So this is going to be this. I think, okay, let me stop here. And so now I have another set of notes I want to look at. If I can get them. I'm actually using my backup computer. I'm trying to get rid of my computer, the new one. Now I'm using the old one again. Very dangerous. Very dangerous. Oh, you know what I mean? Very dangerous. sometimes it works, sometimes it doesn't. So this is the idea of the one where you have, now what type of a tree is this? What's the order? Looks like a what? Looks like a tertiary, right? Because you have 3. So notice this one has 2 children, so you have 1 key. Less, more. This one has 3 children, so there's 2 keys. Less, in between, more. This one is more, and this is going to be less, and more than this one. Easy enough, right? So typically a B tree is a search tree. Now, so the order is 3. The reason we're talking about B trees is because nobody really uses B trees when they have an order of 3. By the way, a B tree which has an order of 3 is referred to as a 2-3 tree. That's what it's called, 2-3 tree. That means that every node can have either 2 children or 3 children. It's called a 2-3 tree. And actually, it's a kind of a cool tree instead of binary trees because it's always balanced. So, the invariant of these trees is that they have to have certain properties, and that is the root is either an external node. External node means it's essentially an empty link, or it has 2 and m children, and all non-root nodes have between m/2 ceiling and m children. Typically, the order that we have these trees is large, like 256 or 512. And the reason it happens, as you're going to see through our analysis, is because a tree of a very, very high order, a B tree of very high order, does not grow very often at all. It can take a huge variation in the number of keys and nodes and not change its height. For thousands and millions of keys, it can just stay the same, as long as we keep this n high enough. And you'll see the analysis of that, which is quite interesting. Okay. So this is going to be our little analysis here that I want to show. So the B tree is based on the height of the tree and its order m. So the height of the tree and the order m. So what we're going to do is we have to differentiate 2 things. There's the number of nodes and the number of keys. The number of nodes and the number of keys. The number of keys is always greater than or equal to the number of nodes. Right? And typically much greater. Because if m is 256, right, then the number of keys can be huge. Okay, so the root has a minimum of 2 children and 2 keys. Now, all other nodes, meaning internal nodes that are not root, have a minimum of m/2 ceiling children and m/2 ceiling keys. So here is our analysis. So what we're going to have is we're going to look at a minimum B tree. Now, what that means is we're going to analyze the smallest or the less dense, the least dense a tree can be when it is minimum and has the height h. So we can take a look, basically, depth 0 is the root, so we have 1 node. The root must have, at minimum, 2 children. So since this is a minimum B tree, we'll give it 2 children. So therefore, there are 2 nodes at depth 1. Those are the children of the root. But once we pass the root, or the children of the root, then we're going to have the number of nodes has to be minimum of m/2 ceiling. Now, if m is even, you don't need the ceiling. The ceiling is only needed when m is odd, which is virtually never. But I'm keeping it in there just for the heck of it. So you can see, so this is the number of nodes at depth 2, depth 3, and then depth h-1, and finally depth h, which is basically all external nodes. These are just null pointers. So we go from 0 to h-1. That is the number of nodes. So how do I know how many nodes that's going to be? Well, all we need to do is to sum all of these. And so the number of nodes, I'm taking the root out of it, can be solved by the geometric series, and you can clearly see that the ratio of the geometric series is m/2. So we start with 2 times m/2 times m/2 again to get this, times m/2 again, continuously, like this. So we have a geometric series, and the series is going to be simply solved by 2 times, this is going to be m/2 to the h-1 minus 1 over m/2 minus 1. That is the expression for the minimum B tree, order m, height h. Now that might not tell you anything, but it will momentarily, because what we're going to do is we're going to apply this result to a specific tree size. So when m is equal to 512, that means that the number of children is 512 at maximum, and the height is 4, we have 64K nodes. Okay? When the height, when the same order is preserved at 512 and height goes to 6, the number of nodes goes to 4 billion, 4 giga nodes. Does that make sense? And I do this simply by plugging in these values of m at 512 and h of 6. So plug this in for m, this for h. So that's sort of impressive. It's sort of impressive because a tree of height 6 has 4 billion nodes. It's impressive. But it's sort of impressive because when we analyze what we are more likely to experience, it's going to be even more impressive. So this tree is very unlikely to occur. Because this tree, what's the probability that we're going to have a tree and we're always going to have the minimum number of values, of nodes in it? Very unlikely. These trees just don't grow like that. What's the probability it's going to be maximum? Very unlikely. What's likely? Something in between. So the number of keys, so continuing with this, the number of keys, basically all I have to do is take this and multiply it by the number of keys. So I simply took our old expression, multiplied by the number of keys per node. Again, I'm including the root because the root's special. And so what we're going to get is we're going to get this value. It's very, very simple. Okay, so n min is going to be this value, 2 times m over 2 to the h minus 1 minus 1. And therefore, this is the result that we get. So now, if we look at the number of keys in the same minimum tree, when height is equal to 4, the minimum number of keys is about 32 million. That's a little more impressive, 32 million for height 4 and height 6. We have 2 trillion keys, 2 trillion keys, height of 6. 2 takeaways, that's a lot of keys. Number 2, that's also a pretty big height. Height 6 is big. What do I mean by big? I mean if that tree is going to stay on disk, then that's a lot of disk. So I don't think that we're thrilled with 6 as the height of the tree when m is 512. But that's not something to worry about. So just in case you're wondering, so after we go past tera, from giga to tera, we have peta, exa, zeta, iota. These are going to be times 1,000, times 1,000. So peta is going to be the next hard drives you're going to be buying. You know, your kids will be asking you the questions like, what did you do before you had a 16 peta byte drive, Dad? How could you store all of your virtual reality games? They're not going to understand your answers. Okay, so now what we're going to do is we're actually going to go and calculate the maximum height of a tree given its number of keys. This is a very interesting calculation because we know that since we have this as a calculation that we have h minus 1 is less than this value right here, so we can solve for h. So h of t is going to be less than or equal to the log, and the log is going to be, because it's a minimum tree, a tree basically is going to be the height of the order of the log of its order. Like a binary tree has a minimum height of log base 2 of n. So a B tree will be log base of its order, which is m, but because it's minimum, it's m over 2. And that's what we get, log of m over 2 of n plus 1 over 2 plus 1. So when k, in this case, is equal to 2 to the 45 power, or 32 tera keys, the height is going to be less than or equal to this expression, which is approximately equal to this, which is equal to this, which is about 5.5. So 32 trillion keys are going to generate a height in the minimum tree of 5.5. Now let's look at the maximum B tree. Fortunately for us, it's much easier to calculate the maximum tree than even the minimum tree, even though they're not too hard. And again, you start with one node, but if the order is m, you immediately go to m. And then you keep multiplying it by m for each subsequent level. So when we sum it, we basically have a sum geometric series, but now the geometric ratio is equal to m. So we get m to the h over m minus 1. The number of keys is equal to m to the h. And so now, if we look at it, the minimum number of keys, this is a reprise from before, and this is the maximum number of keys. So this is minimum, this is maximum. So let's go back to calculate. So basically, if the height is equal to 4, the minimum tree has 32 million keys. The minimum tree. And the maximum tree has 64 billion keys. That means I have 2,000 times as many keys in the maximum tree as in the minimum tree. Right? 2,000. That's very impressive when you consider the fact that I just added, how much is 64 billion minus 32 billion? That's a lot. So 64 billion minus 32 million. That's a real lot, because think about how much is 1 billion? 1 billion is 1,000 million. So that means I added more than 63 billion keys to this tree, and I didn't grow once in height. That's extremely impressive. And the number of keys could be as much as 64 billion. That's keys. And the height is still 4. So it's very clear that a B tree is the perfect candidate for a multi-level index, where basically the tree itself, you come into the tree and you're looking for certain values, and then so you go into the root, and then you follow one of the m children, and then you follow one of the m children. And if the height is 3, you just go to the file and find out what you're looking for immediately. This is not so interesting. How do we find the ratio of maximum to minimum number of keys? Okay, it's not so interesting, so I'll skip that. All right, so that's that. And the other thing that I wanted to talk about, if I find it here, okay, and the last thing I want to cover is I want to cover something called extendable hashing. I'll do it as soon as it lets me. Okay. This computer is definitely quirky. Really quirky. So what is extendable hashing? Well, first of all, everybody knows what hashing is. Hashing is a way to store stuff in tables, either files or memory, and access it by a key, which is hashed, gives you a location to start searching. Right? That's what hashing is. So extendable hashing is something, well, first of all, why do we need anything other than ordinary hashing? And the answer is very, very simple. If we have, for example, 1 billion records in a file, 1 billion records, so, and each one is a K, so now we have a terabyte file. There's no way I'm going to be searching this terabyte file. So I'm going to use hashing so that I can take a key, hash it, it says start looking here. I go to that location in the file, I find it if I'm lucky, if not, I find it by some of the other techniques. Sometimes we can do linear probing, sometimes we do quadratic probing, sometimes we have chaining. Sometimes I may have an overflow area, so basically records that collide are immediately put into a separate area. Okay, so there are different techniques to do that. But I know that if I'm going to have a billion keys, then my hash table has to be, bigger than that to accommodate some of the possible collisions. It has to be a little bigger to get a good packing density. So I'm going to take my 1 billion and divide it by 0.75 to get a 75% packing density size. Once I get that size, that's what I use, and I hash into it. Even when I have 3 records, I still have a gigantic table because I know more are coming. Extendable hashing says I don't know how many more are coming. I could have 1,000 elements here, or I could have 35 billion elements here. I just don't know. In fact, it could change. It could go from 10,000 to 5 million to 2,000 to 35 million. It's just crazy, just going up and down. So that's a problem, because basically, if you cannot simply allocate things for the one rare occurrence that all of a sudden the number of entries in your hash table blow up and go very, very high, and all of a sudden they go down low and they stay low for years. And all of a sudden once they go up higher. So if they're going to fluctuate a lot, you don't want to waste all this memory by having crazy amount of wasted space. So we're going to use a technique which is going to use, I'm going to skip this in here, basically what we're going to do is we're going to create a situation where we use the base 2, radix is a base 2, commonly used as in the hashing approach. And we're going to use the techniques of buckets. And buckets are basically, buckets will be holding multiple occurrences of many records. And so what we're going to do is we are going to generate, through hashing, only enough of a hashing result that will differentiate which bucket to go to. Initially, I will only start with 2 buckets. So I'll have bucket 0 and bucket 1. And what I'm going to do is, and let's say these buckets take 8 records each. So the first record comes in, I hash it. I'm only going to get from my hash the last bit of that hash result, 0 or 1. If it's a 0, it goes into this bucket. If it's a 1, it goes into this bucket. You can see they're going to get, so again, because this is random, it's sort of equally likely that I'll get a 0 or 1. So if I hash the first 8 records, there's a pretty good chance I'll have 4 and 4, 3 and 5, 5 and 3, could be 6 and 2. It's very unlikely I'm going to get 8 and 0. Right? Probability is very, very low. Possible. Very, very low. So what's going to happen is we're going to create sort of the logical view is going to look something like this. So notice that basically what I've done here is a record comes in. If the first bit of the hash is a 0, it just goes into a bucket. But if it's a 1, I need another bit. So really what I need here, because this requires 2 bits, and this only requires 1 bit, I need a 2-bit address for this extendable hashing approach. And so what I'm going to do is I'm going to use 2 bits. But what happens is essentially this bucket is acting like the 0, 0 and the 0, 1 bucket. And this bucket is 1, 0 and this is 1, 1. Why are there 2 buckets here? Well, apparently what happened was my 0 bucket didn't get full up, but my 1 bucket got filled up. And so what happened was that 1 bucket got full up. So what I did was I split it. Why did stuff go into the 1 bucket? Because the 1-bit hash says go to the 1 bucket. Then it filled up. So then I split it, and I took every one of those 8 records, and I hashed them again using 2 bits. So they're probably going to be about 4 here and about 4 here. But the 0 bucket never split, so I didn't create another bucket. Does that make sense? So you can see here is kind of like a tree that's telling me what bucket to go to. A tree is not convenient, but so now basically this is the logical way we look at it. Basically we only need 1 bit for the 0, but really we should think of it this way. Basically, even though we only have 1 bucket, we're going to go 0, 0 to A and 0, 1 to A. That's sort of the more full way of looking at it. But the weird thing is that this index is kind of multi-level, but it doesn't have to be, so we can actually squeeze the whole index into an array. So we have an array. So notice that 0, 0 points to A, 0, 1 points to A. It's a little bit off, but 1, 0 points to B, and 1, 1 points to C. So now the index, which looked like a tree, full tree, by the way, and you know that a complete tree can be an array, so a full tree can definitely be an array, so therefore this becomes an array, index. So what we have is, this is index 0, 0, 0, 1, 1, 0, 1, 1, and in the value it has an address of a bucket. Where's that bucket? Probably on a file. Now, suppose that we keep adding records. Probability tells us that it's very likely that these buckets are about half full after the split. This one is probably more full. It probably has 7 records, maybe already 8 records in it. So it's possible that another record will go in which will fill that bucket. What's going to happen? It's going to split. And when it splits, we split A into A and D. And we will then rehash everything from A, which is, some of them are going to, 0, 0s are going to go into A, 0, 1s are going to go into D. So again, we're going to split that information. Does that make sense? So now we require a 2-bit address. So whether I'm storing or searching, if I'm searching for somebody, somebody gives me a key, I go to the hash function, I say, please give me a 2-bit hash. Now 2-bit hash doesn't mean it does 2 bits. I mean, I'll show you exactly how the hash works, or can work. But it just means that you need 2 bits. If you need more, I'll give you more, but 2 bits are enough. What happens, for example, if B overflows? Keep in mind, this is A, this is A, this is B. So what happens when B overflows? Notice that B is 1, 0. Well, when 1, 0 overflows, that means you're going to have to split 1, 0 into 1, 0, 0, and 1, 0, 1. Which means that you're going to force a 3-bit address across the whole index. So the whole index is going to go from 4 locations into 8 locations. So so what we're going to have is 1, 0, 0, and 1, 0, 1 will be B and it's split. And there's B and there's it split. Here's 1, 0, 0, here's 1, 0, 1. Notice that the bucket C is still taking 1, 1. So it's 1, 1, 0, 1, 1, 1. Now it's a 3-bit address. Any questions? I'm so glad my display is working so much here. Imagine doing this on a board, it'd be tough. That's why I should do handouts, years ago. Anybody know what a handout is? It's not when you're asking for money, but so you give a piece of paper. You should always photocopy before class to make sure everybody, because otherwise you can't do this kind of stuff. All right. Now, this is actually code. This is code that I wrote that shows you how to create a bit index. And I don't care if you understand the code or even want to look at the code, but it's very nice. So basically what it is you want to make an address. And so to make an address, you give me some kind of a key, and a key is a string of characters, and you give me the depth. Depth is the number of bits you want. So the first thing it does, it goes to the hash function with a key and gets a crazy value. And then what it does, it starts ripping that crazy value literally bit by bit, for as many bits as necessary. That's all it does. So, example using the previous page, if I hash Bill, for example, I'm going to get that sequence. Here's Lee, here's Mike, Mark, Alan, etc., etc. So, example, make address Mark 3. So notice what's going to happen is it's going to give me the return value. I don't know why it's all zeros, but I guess it is. It's really strange. Return value is going to be left shifted by 1. Okay, and then what we're going to have is we're going to take the low bit and mask it with all zeros and the 1s. And so the low bit is going to be hash value. This is a bitwise AND with a 1, which is all zeros followed by a 1. And so this just shows you how so what you're going to do is you're going to get some random data. Whenever the directory, and sorry about the arrows, they're a little bit off, but you can sort of see the way they're working. These are all going to one bucket. This is here, 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 so you can sort of align them. Whenever the directory cannot accommodate a new bucket, it's split and doubled in size. So the directory is doubled in size, not the buckets. The buckets are always the same. So you can see that as we start filling in the buckets, what's going to happen, they're going to start splitting, and the index is going to go from 2, 0, and 1, to 0, 0, 0, 0, 1, 1, 0, 1, 1, to 4, to 8, to 16, to 32, to 5, 12, to 1,000, to 4K, 16K, 32K, 64K. It could be gigantic. It could be any size. And the buckets And the buckets could be anywhere. They don't have to be contiguous in a file. They could be anywhere you have space on a file. You just create the buckets. Hey, I need another, let's say a bucket is eight records times 1,000, let's say 8K. I need another 8K. So you just create a new bucket, and you enter it in the directory. So you can see how this hashing is still hashing, but it's extendable because basically after I start shrinking the directory, I'm going to be returning some of the buckets back into operating system. So if B, right now we have B, which is the fifth, 2, 3, 4. B is 100. If this overflows, we have to go to a 4-bit address, which means our array is going to go to 16. Okay? So the deletion of records involves combining buckets and possibly decreasing the directory size. Deletion of records involves combining buckets and possibly decreasing the directory size. Possibly. There's a concept known as buddies, buddy buckets. Buddy buckets are two buckets that are only distinguished from each other by 1 bit. Okay? So here, we're going to look at B and E are buddy buckets. Where's B and E? Sorry. Here it is. So, so you can see the first 8 are here. 1, 2, 3, 4, 5, 6, 7, 8. Then we have this one and this one. So this is B and this is E. Notice that's 1, 0, 0, 0, 1, 0, 0, 1. They're buddy buckets. Now, what's special about these buckets? I think what's special about B and E is that they're the only buckets that are 4-bit buckets. You see what I'm talking about? They're the only ones that are 4-bit buckets. What's going to happen after I delete everything from B? When I delete everything, I no longer need B. How many bit address is this? It's a 4-bit address. Does it have a buddy? Yeah. You always, whenever you have a 4-bit address, it's guaranteed that there are at least a pair of buddy buckets or more. Guaranteed. Why is it guaranteed? Because if you didn't have a pair of buddy buckets, then no buckets would need 4 bits. Well, if no buckets need 4 bits to distinguish them, then why are you using a 4-bit address? So there must be at least a pair. But there could be 2 pairs, 3 pairs, 4 pairs. So we must keep track of how many buddy buckets are going at the 4-bit address. And so since B and E are a buddy pair, when B is completely deleted, guess what? That bucket is returned, and we go back to a 3-bit address. So we're going to shrink the directory, and we're going to reduce the number of buddies. Okay? So B and E are buddy buckets, each requires 4 bits. No other bucket requires 4 bits of address. But of course, it's possible that you could have that. So for example, notice that you would need to add, so let's look at this one right here. How many bits do I need for C?